Hi, this is Professor Scott Sampson again in another of the series of Discover AI. And today's topic is from Chapter 5, Large Language Models in Various Sizes. That's what we're going to talk about today. So, the issue that this is part of the module for is selecting a large language model. And there's a lot of different models out there, and they have different abilities and different costs and things. And that's what we'll look at today. Is the size of the model and how that influences performance and how that influences outcome. This is actually a DALL-E prompt from 2004, the sad time when models had a hard time counting number of fingers and making faces accurate and things like that. We've come a long way since then. This is being recorded in early 2026. Okay, here's a newer one, Nano Banana, for more than a year later, so much better detail on things. So. Okay, so there's different factors to look for. I found this thing online. I thought this was actually useful here. Factors to look for in an LLM. Parameter size, that's a big issue. Window context, focus area, customization, license, and offering. So in the prior chapter, we talked about open source versus proprietary models. That's the licensing issue. Has to do with that. We'll talk about customization in a later chapter. And in this chapter, we're going to talk about parameter size and context window, two really primary elements that we have to decide about in selecting large language models. So we talked about before this idea of the neural network, and where we pass through the network all of the embeddings, and they go through the input layers, hidden layers, which do feature detection, to the output layers. And so the examples that I gave were all relatively simplistic, like this little graph that you're looking at here. Relatively simplistic, not a lot of perceptrons there. The reality is that these models have a lot more complexity than this and a lot more perceptrons. The little lines here represent the weights. And so this is a comparison looking at some from 2018 to 23. And it was interesting because I can remember back in the early days when GPT-3 came out. So in 2018, GPT-1 had 117 million, which seemed like a lot of parameters. Then GPT-2, 1.5 billion, GPT-3, 175 billion. So I don't remember exactly when it came out, but I remember when they announced this, that it had 175 billion parameters. And I thought, what would you ever need 175 billion parameters for? We've gone a lot greater since then. GPT-4, 1.76 trillion reportedly. It's a proprietary model, so we don't know for certain. But and then the human brain is estimated to have something like 100 trillion parameters. So we're not even close to the human brain yet. I shouldn't say parameters, but they're the synapses and the connections between brain cells. I think this is a report about GPT-5. GPT-5 uses a mixture of expert model, and this article from Medium.com, they estimated that it had 52.5 trillion parameters. Now, back in chapter 3, we talked about mixture of experts. What that means is that we don't actually have to, in inference, we don't actually have to calculate all, across all 52 trillion parameters or weights of the model. So mixture of experts is very nice because it allows us to divide up the work into smaller submodels. Mixture of experts, we talked about that in chapter 3. And it also has a 1 million token context window, which we'll talk about later today, is context windows and how that matters and why should we care about that. Here's some top large language models from September 24. The top of the pack here was the GPT-4o model. Back in 2024, 7 billion was a small model, and then 35 billion was kind of medium, and then 405 billion was a large model. That's kind of the perspective here. That was again back in 2024. Extra large, so 1.76. I mean, GPT-4o kind of broke rank with other models at that point, but not anymore. Here's August of 2025. And again, one of the things that's interesting is that now we don't know how many parameters they are. If we look at this, for all of these top models, according to this explodingtopics.com blog list, why don't we know about the parameters? It's because they are proprietary models and they just don't let out information about how many parameters they have. And so it's unfortunate. It's interesting, on this list, there's the DeepSeek models, which are open source, and there we know how big they are. 671 billion, but as a mixture of expert models, they only activate 37 billion at any given time. So that's actually not a really big model, that DeepSeek model. It's pretty amazing how well it does with just that few of parameters. The license, it's MIC copyright, MIC license, or MIT, I'm sorry. Sorry, I've been at the gym and high fit and things, so I'm kind of low energy right now, kind of fatigued, but I'll do the best I can for this video. But you're probably watching it at double speed anyway, so that's compensating for my lack of energy. DeepSeek comes in a lot of different flavors and varieties, 1.5, 7, 8, 14 billion, all these different sizes here. And we'll talk later today in Chapter 5 about how we get these smaller models out of the bigger models. They are actually, here's the answer, they are distilled models. So DeepSeek team has demonstrated that the reasoning patterns of larger models can be distilled into smaller models, resulting in better performance compared to reasoning patterns discovered through RL, reinforcement learning, on small models. So holy cow, what a great discovery that is. So what is RL? It's this idea of reinforcement learning. And so using these large models to train smaller models, we have a teacher model and a student model. That's the idea of distillation here. So distillation is so absolutely crucial for us to get reasonably sized models at relatively low cost that have great capabilities. Here's a little bit more information about DeepSeek and its performance. So it was doing pretty well back in the day. Anyway, enough about DeepSeek. All right, some model size issues. So GPT-4 was proprietary, but it's really, sadly, about the last one that we really had much even reasonable speculation about how big the models were, these proprietary models. So here's this article I found on HackerNoon that just went over the GPT-4 model. So again, we're much bigger than this, but it'll give you an idea of kind of the scope of models and how big they can be. So GPT-4, it was some key details about this model. Sorry, let me just thumb through this here. Model stats, 1.8 trillion, actually 1.76 is what was reported. 10 times more than GPT-3. Mixture of experts, we talked about that before. Trained on 25,000 NVIDIA A100 GPUs, which, you know, the retail price of an A100 is $10,000 to $20,000 each. And it took 90 to 100 days. Pretty amazing how much compute that is. Trained on a data set of 13 trillion tokens. We used to think that was a lot of tokens, but pretty typical now. Supports, this is amazing, the context length, also called the context window, or the context size, 32,000 tokens of context. That's pretty, that seemed like a lot at the time, but that's actually not very much, as we will see. Let's see. Training, transformer, architecture, trained on web text, books, Wikipedia, other things, other uses, next generation, modalities. The modality is not a multimodal model, GPT-4. Well, actually, that's not true. GPT-4 was not a multimodal model. It was a text-only model, but GPT-4o became multimodal, so it had ability to handle images and such. All right, other things about it. Mixture of expert, has 16 experts, reportedly, each of them having 111 billion parameters. And at any given time with mixture of experts models, you don't just pick one of the expert models. Often it would be a combination, maybe 2 or 3 of the models would be chosen, and then you do some weighted sum of the results coming out of the models there. So 2, in this case, 2 are activated per inference query, 55 shared parameters for attention, so they actually have some shared across this, so those would be added to the 2 times 111 billion, and that comes up to about 280 billion parameters for each inference pass, which is a lot more economical than 1.76 trillion. All right, scalability, what else from this article? Trained, I already mentioned this, sorry, it's a little bit repetitive. 13 trillion training tokens. 2, this is an interesting number here. So in order to train GPT-4, it took 2 exponent of 25, so it's 2 followed by 25 zeros, that's 10 to the 25th power. 2, now how big is that number? Here we go, here's the number. 2.5 and 20 zeros after that. All right. So if you take that number of floating point operations that were used to train GPT-4, that is 53,000 times more than the grains of sand on all of Earth's beaches, according to Scientific American. Now, that may or may not be true because, you know what, I don't know if anybody's actually counted the grains of sand, but it's kind of an estimate there. But anyway, the point of it is this is a lot of calculation to train one of these models. Runs on a clusters of 128 A100 GPUs. Parallelism, tensor, latency, we'll talk about that in chapter 6. Speculative decoding, okay, dense inference clusters, okay, that has to do with how much useful data we have within the network, I believe. All right, why do we have big models? Why do we need such big models? So, Claude 3, that was a prior version of Claude. At this writing, we're actually up to Claude 4.5, but Claude 3, we had Haiku 20, Sonnet 70, Opus 138 billion parameters. I have a later slide that we'll see about some of their more recent models, but I don't have any idea of how many parameters the more recent models have. So sadly, as time has gone on, the foundation model creators have become more and more secretive of what they do. But the idea is that the bigger models were smarter at different metrics. So here's different benchmarks, and we can see that the Opus model was smarter than Sonnet, which was smarter than Haiku. So that's kind of how it works. But still, you think about this, the cost is a lot greater, as we will see later. One of these, the first one on this list here, is the MMLU. This will come back in chapter 6 when we talk about metrics and benchmarks. It's kind of a common benchmark for large language models. Mid-2024, here we have again Haiku, Sonnet, and Opus. The thing I want to point out here is the pricing difference. Look at this. Haiku, input token, 25 cents per million tokens. Sonnet, $3. Opus, $15. That's a lot more money. Okay? $75 per million output tokens. That's actually pretty pricey there. So anyway, that's what happens, is that the big models cost a lot more for inference. Okay, January 2025, same kind of idea. You know, bigger models cost more money. All right, MMLU, 57 different subjects. I should actually put this in chapter 6. It's just pointing out MLU that you want to have higher performance and you also want to have lower cost. Okay, cheap and smart models. Okay, low rank adapters. So one of the things we do, training models is so difficult, takes so much effort that if we want to retrain them or train them on new tasks, we just can't afford to spend 90 days, you know, with 25,000 A100 GPUs. That's just not, you know, reasonable. So what we do is we use low-rank adapters. So I actually prompted for what is a low-rank adapter, and it gave me a description of this. Let me just tell you what this is. Read it on your own. Just go to your favorite large language model, ask what a low-rank adapter is. Let me just tell you kind of visually what I think it is, or what it is, you know, actually. So what you do, I found this diagram online, this little animated thing. You have at the bottom of the model, you have the input data. So that's your input, you know. Basically, it's the prompt and context that you tokenize, embed, and you do positional encoding and such. So you have the input data. On the left is the pre-trained weights, which are the weights of the model, kind of symbolically represented. The matrix of weights is not actually, you know, this shows it D by D dimensions. That's not how it really is. It's not actually a big square matrix like that. But anyway, you feed it into the model. But what you do with a low-rank adapter is you feed in you feed the data into the regular model that's been pre-trained, and then on the right, what it's doing is it's creating a summary. It's a scaled down using some matrix multiplication, a smaller rank. It's a smaller matrix, and all you're doing is training this little smaller matrix here, and you get the output. And then when you're done, you sum the things going through the main part of the model and the small part of the model. I have another diagram. Maybe this is more helpful, or maybe it's not. So there's the output data. D is a big dimension here, and then R is a small dimension. So you're just training a small piece. So this other diagram I found about this is slow to train a large matrix. And this is 2048 by 2048. That is not a large matrix, but it's relatively large. But what you do is instead you using matrix compression, you get down to a 4 by 4 matrix, and that's very easy to train because it's very small. So that's kind of the idea of low rank adapters. It's just basically we use low rank adapters, and I think we'll see these used in the future to allow big general purpose models to be able to be specialized on important specific tasks. All right, so what does it buy you? You know what? I'm going to skip this slide. Too much information. Skip this slide. Too much information. All right. Context window. Here we go. Fred Flintstone, the tiger jumping through the window. All right. Context window, context length, context size. So context. What do PCN diagrams depict? So I took this on an early model, GPT 3.5. I said, what do PCN diagrams? And it just hallucinated like crazy. It said something about process connectivity network, which is actually an abbreviation coming from PCN. And it talked about a bunch of things that I don't even know where that came from. All right, so what we do is we give it the prompt, and then I also gave it my book. I gave it some chapters from my book as input. And that went in with the prompt into the context window, and the result was almost perfect. You know, it was so great, maybe even perfect. It was a great result. And this was from a relatively crappy model, GPT 3.5. It was great in its day, but now it's been far surpassed. But the point of this is, if you just give a prompt to a large language model, it's kind of taking your chances about what you're going to get as a result. Whereas if you give it context, it will draw on that context to help lead you to truth. All right, so what is context? There's the 6 blind men and the elephant. Although this is weird because they're not 6 blind men. There's just a bunch of people kind of looking at the elements. I don't know why I even got this picture. Anyway, it's help for answering a prompt. So what does it mean? What is context? It's what you're looking at. It could be a document. It could be look up from a vector database, which we call retrieval augmented generation. Search engine result page. We could look it up on the internet and find out context. Examples, which we call short prompting. We'll cover that in chapter 9. Anything that will help the LLM figure out the completion. So we have various kind of tools we call that give us information that helps us answer the questions. So if I ask a large language model, hey, what's the weather forecast going to be tomorrow? The only way it could possibly know that is if it looks it up somewhere on a current source. It would not know that from the training data that may have happened months or years ago. All right, the context window is how much context you can feed into a large language model at one time. How many tokens? And remembering that tokens are not the same as words, that some words have an exact token representation, but other words have to be broken into more than one token, especially things like maybe proper nouns or stuff like that. If the context is more than the context window, it just cuts it off, it forgets it. Although there are techniques we use now to kind of have a dynamic context window. We'll look at some of those, I think, in a later slide. So here we have a multiple iterations. In turn 1, we have an input and then the output. And as we know, because of autoregression, we take the input and the output from the first step of this process, and we feed that as the input to the next one, and we get the output. In this case, is kind of a not most accurate representation because the output of a large language model is a single token currently as of 2026. And so, but anyway, those go back into the model, and then you have some reasoning tokens. This is dramatically underrepresenting the reasoning tokens in this picture because reasoning tokens can be the far majority of the tokens in a particular example of inference. Then you have the output, and then what happens is there's a point where it cuts off the output. Actually, this is not a completely accurate diagram here. As I understand it, it would not truncate the output, it would truncate the beginning of the input. It's probably more representative there. But anyway, you get the idea though. The idea is that the context window is how much data the large language model can ingest at one particular time. Remember that the input prompt goes in and the output prompt response also goes in with the input token. That's the autoregression idea. A token at a time. Therefore, the context window needs to include the input and the output and reasoning if it's a reasoning model. So that kind of puts demands on having a good-sized context window. And I mentioned that one of the early models what was it, GPT-3 or 4 had an 8,081.92 token context window. That's almost nothing. That's a very tiny context window. Here's some examples. Historical, we have GPT-1, 512 tokens. That's not much, you know. GPT-2, it doubled that. GPT-3 doubled that. GPT-3.5 doubled that. GPT-4, the original one, doubled that. For their new one, actually quadrupled that. Holy cow. 32,000. Now we're getting into more reasonable space here. GPT-4 Turbo, 128,000. More. GPT-4o, their Omni model, 128, the same. Their Mini had the same. So we're kind of at a plateau there. But then something happened in 2024. We started to see this thing happen. So here we got 200 for their O1 model, which is not a GPT line of models. It's still a transformer model, but I believe. But anyway, the O1 model had a bigger token window. And then here comes their Mini, back to the 128. In early 2024, Google came out with Gemini 1.5 Pro 2 million token context window. See, you see that leap there. Now, they did it through some creative ways. They managed this context window. But that's something we think about is, wow, a 2 million token context window. What do you put in such a large context window? Well, one of the things, and this is the supplement to Chapter 5. I hope you had a chance to read that. But it talked about, there could be things you might use such a large context window for, but in some cases it can be detrimental. And so, do you really need that much context, or you're just throwing a bunch of garbage in? One of the issues that comes up is this issue of context rot. And it's the idea that if you have too much context, sometimes you lose track of things from a long time ago. Things that were, perhaps early in some particular prompt chain or something like that. And this diagram, which is from this research, trichoma.com, context rot, was basically some evidence suggesting that the accuracy of large language models, different models, that it goes down based on how many tokens you feed it in the context. And this goes up to 10,000 tokens. And this is not the actual chart. If you go to that Trichoma website, you can actually see the actual chart from it. It's not kind of as artsy as this one is, but you get the idea, though, is that sometimes too much context can cause a problem. Now, I don't want to be alarmist here about this, because I've just discovered that the context windows have gotten much more robust recently, that you can give them quite a bit of context and they can kind of keep things straight. But there can be the problem where you give it some information that might not fully be relevant and it gets confused about some of this information. There's also, about using these large context windows, there's serious cost issues. So do we want more tokens? In an earlier session in my classes, we did this little tokenizer thing. Do we want more tokens? We do want to have more tokens go through the model, but only to a point. So you pay for tokens. That's one of the key things to understand, is that when we're accessing large language models, if you do it through an API, you almost always just pay for these tokens. It is possible to subscribe and get some rate limits and things like that, but typically we pay for tokens. We have the input tokens, that's the input prompt plus the context. We have the output tokens, how much it produces, and that leads to the cost. So here are some examples of some 2025 models. GPT-4o, input $2.50 per million input tokens. It sounds like a lot of tokens, but with a lot of context, you can burn through that pretty fast. $10 for a million output tokens. That was a little pricier than some. There's some of these mini models. Let's see, do we have the bottom one? It's a O1 mini. It's actually still pretty pricey. The O1 model, $60 for a million output tokens. Wow, that is pricey. Your DeepSeek prices. Now, DeepSeek is open source, but you can also go to a website and actually do inference in the cloud. And if you look at this one, holy schmoly, look at this. DeepSeek chat, input tokens, 14 cents per million. Output tokens, 28 cents. That is a well-priced large language model. That issue of cache misses, they'll come up in Chapter 9, but if you actually hit the cache, you can save 90% of the cost for a lot of these models. So that's a topic for another day. What's going on here? So The question is, why are input tokens cheaper than output tokens? So again, I want you to think about this. I have another chart to demonstrate this here first. Is that we have, these are some models from, kind of January of 2026 when I'm actually doing this recording. I'm in the same month here. But we have large, medium, and small models from different vendors. And look at those prices. The large models are all significantly more expensive than the medium models, which are significantly more expensive than the small models. So man, we love these small models. There are these meta models that are actually free because they're open source, but you can also pay companies that will do inference on those models. And look at these context windows, 400,000 for the OpenAI 5.2 and 5 models, $1 million for the Google models. You have to pay for it. So that Gemini 3 Pro, it's $2 for $1 million input tokens or 12 for output, unless you exceed their 200,000 token base limit, in which case you start paying quite a bit more for tokens, input and output. Claude, sorry, I'm spending probably too much time on these issues. That's why I do the recording, so you can fast forward over this. They do point out, this was interesting, I saw this on a Claude screen a while ago. Long chats can reach your usage limits faster. It's not just what you chat, but if you don't clear and do a new chat, everything that's in that particular thread will go in the context, as much as it can cram into the context window. And that's going to be very detrimental on, your ability. You're going to hit your usage limits. They basically count how many tokens you use, input and output. There's a cap on that. So, all right. It rereads the entire conversation, including large attachments. So if you put a big attachment in with your prompt, man, that can really consume up your context window very fast. Oh my goodness, this is going on too long. Sorry, these are some leftover slides. I thought I hid some of these. GPT 1.5 Pro, there's again the prices. You have a free tier or pay-as-you-go tier. They have rate limits, 2 requests per minute, 32,000 tokens per minute, 50 requests per day. Wow, that's not very many. So, try before you buy. The idea is that you come in with the cheaper one. Again, this is mid-2024. Come in with the cheaper one, and then at the bottom you'll notice it says prompt responses to improve our product. Yes, if you use the free tier, it may be free, but it has limits, and they will likely use your prompts and responses to help train their future models. So that's kind of how things work. What's the context window size? Oh my goodness, I don't even see it here. Is it here? Well, it doesn't really say. Gemini Pro comes with 128. Well, if you look on the right side, it does say there's a price you pay for prompts up to 124,000 tokens. That's kind of the regular context window size. But they have it 1 million. You can pay more for that for larger context. They tested up to 10 million tokens in theory. Okay, why are they cheaper? It has to do with the extra processing needed to handle large ones. Actually, this thing here, this is from this company Magic. I think they kind of died here. I'm gonna skip this. Huge context windows, summarizing large corpuses. Okay, question and answers. Yeah, from the chapter supplement, you'll see I'm a little bit, pessimistic about the use of massive context windows. Sometimes I think it's just if we're using that much context, we're probably sloppy in our context engineering. All right, onward we go. Reducing the model footprint. By the way, you're welcome for my students that I don't cover all this stuff in class. Holy cow, that would be serious, headaches. How do we get the models to be smaller? I'm just going to mention a few ways. One is quantization. Quantization is great. You reduce the precision of numbers. So, for example, the number 126.35, that may be a weight. So actually, this is kind of weird. This is not on the node there, but that's actually a value there. But what you do is it's actually the weights themselves. Instead of represented as 126.35, you represent it as 126. So you have less precision in your numbers. And the advantage of that is that you can cram more numbers into a certain amount of memory, and so it can actually be faster. So the left is before quantization, and the right is afterwards. You just basically round everything to the nearest whole number. That's not the only way you quantize, is removing decimal places. It's usually how many bits it's represented in each weight. That's how you quantize. So you might have a 32-bit number, and you drop it down to an 8-bit number. Okay, so a lot less precision, but the models can still do pretty well. All right, you have another technique. This is very, very common. Distillation. You have a teacher model, big model. Now this is symbolically a big model. A big model is trillions and trillions of parameters. Then you do knowledge transfer, and then that goes to a smaller model. So it's kind of like training the model, but instead of training it with some big corpus, you use the teacher model to train the smaller model and have it represent roughly the same type of knowledge and information that's in the bigger model. All right, trained on unlabeled data. Very costly. Oh, sorry. Create soft labels for the data. So you basically, the thing you pass from the big model to the little model is actually probabilities of tokens. And that's a great thing. It's very useful and helps to train these. Student models are fine-tuned on labeled data. So much cheaper than having to hire a bunch of humans for reinforcement learning by human feedback. Another example, we have a teacher model, and then we have these labels, and then we supervise train a distilled smaller model called the parent model, child model. Yes, usually though we think of it as the teacher and the student model is the way we think of these. Okay, already mentioned that. Fine-tuning on labeled data is very efficient. That's kind of the way it works. Another one is pruning. Sometimes we have the weights that are, they may, like in this example here, I have the original model, but we found out that some of the weights are near zero. So what you do is just get rid of them. If a model is near zero, sometimes if you make it equal to zero, it doesn't really affect the model's performance. That is the end of chapter 5 and 5C. So you can stop the video now. What are we at? 32 minutes. That's probably enough. Although that's only 16 minutes for you double speed people. But I have a few more slides here that are just kind of some review things that have to do with model size. I do like to integrate things and tie them across different chapters. So feel free to shut this off if you're done or if you want to watch this. Again, from chapter 3, we talked about large language models, not the system. And we have these different elements. We have these data resources here, and then we have the model. That's two of the ways in which the model understands things. And we cannot forget the importance of retrieval augmented generation, because what it does is reduces the amount of data from a particular corpus that we would then feed into the model as context at the time of inference. And so we just basically look up in the database those little pieces we need from the embeddings that are in that vector database. Wow, how great is that? All right, mixture of experts. We already talked about this a little bit more. This is from chapter 3, but again, it has to do with model size because it makes large models be much more efficient. So here we have the example of the little gating network, and the gating network takes the prompt and then decides, okay, let's pick some expert networks and then let's weight their outputs in order to calculate the output that's actually used and passed on to the user. Multiple large language models, trained with specific tasks. Output is the weighted sum. There's just a lot of these that are out there. This is funny, I should have updated this. GPT-4 is a mixture of experts, but I think I pretty much can guarantee you that the GPT-5 models are also a mixture of experts, as are all the Gemini models. We don't know this for sure because it's proprietary, but I don't think there's any way you can have models that are have this much performance practically without using a mixture of experts. Yeah, it's a diagram of kind of how it works. A little GIF thing. Yeah, I wouldn't sweat about that. All right, advantages. Big model, small compute. You don't have to infer on every expert. Specialize, expert focused, parallelism. You can have 2 experts calculate simultaneously. You can add experts if you need to. Various advantages. Decided on a model size. So I'm going to go to the open source repository Hugging Face. And here we're looking at Hugging Face, and I don't remember when the screenshot was. I should have written this down. But if you see models that say instruct on them, that means they've been fine-tuned to follow instructions. That used to be a labeling thing popular back in the olden days of 2024, I don't think we have to say that as much because most of the models that we use are fine-tuned to follow instructions. Most of the common models that are, popular models today. Here's the model card. So I've selected a particular model. And if you look at this, there's a little thing here. The model is 4.15 billion parameters. The tensor size is BF16, and I think that may be, what does B stand for? Maybe binary, but it's floating point, 16 digits, or, binary digits. So that's actually not a bad, that's not very quantized there. The tensors are arrays of numbers. Okay, so that's when we talk about safe tensors or things. So a tensor is talking about what goes into those arrays there, multi-dimensional arrays. Here's some more models on Hugging Face. Look at all these. Lots and lots of models. They have truly hundreds of thousands, if not millions of models available. And their names often indicate how many parameters they have. A lot to choose from. So not to worry, in the next chapter, chapter 6, we'll talk about assessing model performance. We'll talk about how you can determine is a model actually better or worse at particular tasks and different performance metrics. And my friends, you have survived. Bless you. I hope this was at all useful. And anyway, that's it. If I wind up doing these again, which I probably will, we'll see you at the next of these. Take care.